Good morning.
Good morning.
Good morning.
And how's everyone today? Feeling good for a Monday morning?
We're doing good. How are you?
I'm fine, thank you. So let's see. I've got I think Desiree out today. Anybody else gone? And
Naomi is.
Naomi.
And Sierra.
I have another one next time.
You can turn it.
So Sierra, Naomi, and Desiree. All right. Let's see. Everybody. Everybody there in Joseph City. Okay. All right. So did anyone do anything amazing over the weekend?
We watched the Lady Roadrunners beat Winter Rock.
Heck yeah.
All right. Good job. Congratulations. So next game is today, right?
Yes.
Yeah.
At 4.
So who are we playing today?
Paige.
Page. All right. Turn the page. Time to look past those guys. Okay.
I'm scared.
Well, that'll be awesome. What time is that game?
At 4.
4.
Okay. Well, I think so. We're down to like the last 8, right?
Yeah.
All right. Well, listen. If they get to the final 4, you guys need to tell Futuris pep bus. Start getting a pep bus going because it's been years. It's been years since they've done that. So, anyway. Well, good luck on that. Anything else going on? Anybody else do anything amazing over the weekend?
Naomi and I had our performances.
Oh, in the Camp of Rock or whatever?
Yeah. The Camp of Rock.
Is that what it's called?
Camp Rock, but yeah, you were close.
Camp Rock. Oh, I'm thinking School of Rock, right?
Yeah.
Kind of like the same thing, right?
Pretty much.
Pretty much. Okay. Well, how did that go? Did you feel good about it?
Yeah, it went well. I had to improv a lot
Uh-huh.
because people kept forgetting their lines, and then I accidentally called one of the cast members by their real name on stage.
Whoopsie.
Yeah.
Actually, one of my favorite plays I ever went to, I had a friend that was acting in Death Trap, which is like a murder mystery. And I mean, he was like super precise with his lines and everything. But all of the props kept falling apart on stage. And it was hilarious. And so he had to improv. And anyway, that was one of my favorite. And I was so glad that I like to sit up front for plays and performances. And if I hadn't, the people in the back probably missed like half of the funny stuff.
Yeah.
Anyway.
That's awesome.
All right, anybody else? No? Well, I did see Romeo and Juliet. I thought that was pretty fun. And I enjoy the Shakespearean. I kind of missed them. They didn't do the costumes, but it was a fun show. So that was pretty cool. All right, well, let's go to our 7-2 is kind of where we were. And we were just right at the bottom, just finishing up practice 2B. So I wanted to just say a word about simplifying our answer. We kind of got cut off. And then we will finish 7-2 and maybe go on to 7-3 here today. So anyway, so just kind of looking, we had said that one of the ways that you could actually do the tangent of 75 degrees here is to take the sine of 75 divided by the cosine, okay? And so that's what this is here. So this is the sine of 75 degrees divided by the cosine of 75 degrees. So the answers to the previous 2 problems. And so then we cancel the 4s, or think of it as multiplying by the reciprocal. And we got down to here, all right? But there is kind of a trick that I don't think you've ever seen before. I could be wrong. But see here, radical 2, you can actually factor out of radical 6 because 6 is 2 times 3. And so you probably never factored out a radical before. And so you can factor out a radical 2 from both the numerator and the denominator and then cancel the radical 2's. And so your final answer there would be radical 3 plus 1 over radical 3 minus 1. Okay, so I just kind of wanted to show you that little algebra trick there. All right. So, but were there any questions on that? Okay. Well, oh, I know. Before I go on, I guess I kind of feel like I owe Ricky an apology. And so I want to do that publicly, is that, I was concerned about you having a phone out. And then Jill told me that, Dad, he was just looking up some instructions on how to do it. It was the math stuff. So anyway, so I apologize, Ricky, for getting that after you on that or whatever. And so I appreciate you staying with the lesson and trying to figure out something to do it. But please don't ever hesitate to just ask me, okay? Sometimes your phone can help you, and I appreciate that. But you do have to know, as a teacher, it's really hard. Like if I see Kinsley on her phone or something, I know she's messing around, okay? No, just kidding. But as a teacher, it's kind of hard to tell who's actually staying with it and who's not. Ironically, Jill was telling me that she was not working on the lesson on her phone. So anyway, but I just wanted to tell you that I do appreciate you, trying to figure out another way to do it. So anyway, all right. Well, let's go on to the next part. All right, so the next part is dealing with radians, okay? And so when dealing with radians, it helps to know fractions. For example, like if we're trying to find an exact value for pi 12ths, it's helpful to know that that's pi 4ths minus pi 6. Okay, now I really changed how I've taught this part over the last few years, because I used to really kind of drill into people about, trying to work with the radians. But the sums and differences of the fractions just are so much more difficult than saying, 75 degrees is 45 and 30. So the way I do it now is just say, look, if you know how to do it in radians and it pops up and you see obviously, this is, pi 4ths plus pi 4ths would be pi halves or something like that. If you see it, great. Otherwise, just change everything to degrees. Because I found that when my students just change these problems to degrees, then they have they do way better. They're less likely to make mistakes. So like for this one, so pi 12ths radians, if you just change that to 15 degrees, then you're like, that's 45 minus 30, okay? And so when we're doing those formulas, it just seems easier for students to just change it to degrees. But, so that's kind of how I'm going to model it. So like if I want to find the exact value for sine pi 12ths. So instead of doing this, what I'm going to do is just convert it to degrees and say, okay, that's 15 degrees is 45 degrees minus 30 degrees. Okay. Now you look up. So remember, the first thing is you get the right sum or difference. You get the right angles. Okay. The second thing is you look for the formula. Is there a question?
Yeah, how did you convert it into degrees? Did you just use the unit circle, or?
No, well, you can use the unit circle. That would work, but pi twelfths is not on the unit circle. So that's where you say, okay, pi twelfths times 180 degrees over pi radians. So kind of back what we did in chapter 6. And so then the pi's cancel, and then you do 180 divided by 12, and you end up getting 15 there. So that the conversion between degrees and radians is that 180 over pi, or pi over 180 if you're coming back the other way. Okay? All right. Okay, so thank you for that. So then you say, okay, 15 degrees. The angles that would add or subtract that are on the unit circle to give us 15 would be 45 minus 30 would give us 15. So now we look up the right formula that we wrote down. So this is the sine of u minus v formula. Okay, so then everywhere there's a u, I'm going to plug in 45 degrees. Everywhere there's a v, I'm going to plug in 30 degrees. Okay, so then I have the sine of 45 times the cosine of 30 minus the cosine of 45 times the sine of 30. All right, now you pull out your trusty unit circle, and then we get radical 2 over 2. Cosine of 30 is radical 3 over 2. Minus cosine of 45 is radical 2 over 2. Sine of 30 is 1/2. Simplify those fractions. Radical 6 over 4 minus radical 2 over 4. And then you put them all over one fraction. Okay? All right, so any questions on this example before I have you do the next practice problem? All right, so go ahead and try that. Practice 3. Let's see, what is it? Practice 2C. All right, so Seth, when you've got it.
Is it radical 6 over 4 plus radical 2 over 4?
Yeah, and then you can combine those, since they're both over 4, to radical 6 plus radical 2 over 4. All right, so good job. Any questions on that? Okay. All right, now, so it says sometimes it's helpful to write down the needed formula. If you've noticed, as I go through these problems, I always write down whichever formula I'm going to use before I plug in, because I think that's helpful. So what formula is needed in the next problem? So look at practice 2D and tell me which of the formulas would we need for practice 2D. All right, Ricky. Which formula would we need to do practice 2D?
Is it the cosine u plus v?
Wait, what's the answer to this?
What's the what? He said the right answer.
Never mind, sorry.
Are you on the last problem? It was radical 6 plus radical 2 all over 4.
Yeah, I got that. Never
Okay.
mind, sorry.
Okay, so this is correct. This is the formula. So now go ahead. So write that down, and then go ahead and now do practice D. So you're going to use this formula for practice D. And so in this case, we're actually using the formula backwards from the way that we have been doing it. All right, so Serena, when you've got the final answer, let us know. All right, Serena, are you stuck? You need some help?
I got cosine 1/4 pi.
Which is what?
45.
Which is what?
Degrees.
What's the sine of 45 degrees?
Radical 2 over 2.
There you go. There you go. Okay, so using the formula that Ricky said, see if everywhere there's a u, there's a 25. Everywhere there's a v, there's a 20. Then this is going to be the cosine of u plus v, or the cosine of 25 plus 20, which is 45. And then the cosine of 45 degrees is radical 2 over 2. So this is kind of using the formula backwards in a way, or at least from how we've been using it. Okay? So, but that's a great way to take a complicated problem and then simplify it down. All right. Okay, any questions on that one? All right, so the difference identities can be used to verify the co-function identities. All right, so for example, it says prove the co-function identity cosine of pi halves minus x is equal to sine x. Okay. Now, the first thing I'm going to do is I'm going to do it in terms of degrees or radians. It doesn't matter. You can, as far as proving things. Now, remember to prove an identity like we did earlier in this chapter in 7.1, we're just working with one side and we're trying to get it to equal the other side. Okay? And so here, if I think of this as u minus v, then everywhere there's a u, I'm going to plug in 90 degrees, and everywhere there's a v, I'm going to plug in x. So I'm going to use the cosine of u minus v formula, which is this. Okay, cosine u times cosine v plus sine u sine v. So now I'm going to plug in 90 degrees, or pi halves for u, and for v, I'm going to just plug in x. Okay, so I've got it, whether you did it in radians or degrees, it'll still come out. So cosine of pi halves, or 90 degrees, times the cosine of x, plus the sine of pi halves, or 90 degrees, times the sine of x. And so now I go through and simplify and say, okay, what's the cosine of 90 degrees? That's the x value, so that's 0. Okay? So I have 0 times the cosine of x. The sine of 90 degrees, or pi halves, is 1. So 0 times anything, that whole term is going to go away. So I just have 1 times sine x, which is sine x. And so, excuse me, 0 plus sine x is sine x. So that's it. That's what I wanted. I wanted to show that that all of this was equal to sine x. And so that's how we actually derive that identity, is through the difference identity. Okay? All right, so see if you can do practice 3A. And again, if you want to convert that pi halves to 90 degrees, that's okay. All right, so Kinsley, when you've got it. Or I guess there's really nothing to say. Either you got it or you didn't get it. All right? Because it's the thing about proving identities is you know what the answer is. It's just whether or not you can get it or not.
It is an identity. That's what I got.
Okay, great. All right, would anyone like me to go through it? Okay, so here we have, so we're going to use the sine of u minus v formula. So that's sine u cosine v minus cosine u sine v. So everywhere there's a u, I'm going to plug in x. Wherever there's a v, I'm going to plug in pi halves or 90 degrees. All right, then when we work it out, the cosine of 90 degrees, that's going to be 0 again. The sine of 90 degrees is 1. So then 0 times this that's going to be 0. Cosine x times 1 is going to be cosine x. So we have 0 minus cosine x, which is negative cosine x. Okay. Okay, now, so the next part, okay, where it says sometimes it's helpful to draw a triangle. The next example is probably going to be, in my opinion, the hardest thing in this section, okay? And because we're going to have to draw a triangle, sometimes two triangles to figure this out. So let me just, okay, so because see what we're going to have here is that, see if you have cosine of arc cosine, remember those cancel. But if you have the cosine of the arc sine and these functions aren't the same, the trig functions aren't the same, then you've got to draw a triangle. Okay? So we'll go through that. All right. So here we have, says, write the cosine of the arctangent of 1 plus the arc cosine of x as an algebraic expression. Well, the thing that helps you remember what to do is remember the arc functions, these are angles. So the arctangent of 1, you think of that as your u, the arc cosine of x as your v. Okay? So we need to find the well, first let's apply the formula. So this is the cosine of u plus v. All right, so then the formula is the cosine of u plus v is cosine u cosine v minus sine u sine v. So what's different about these is the u is going to be arctangent of 1 and the v is going to be arc cosine of x. So when you plug in, these look horrific. I mean, this looks crazy. But what you're going to have to do when the trig functions don't match here, you're going to have to draw a triangle. Okay? Now, where they do match, see cosine of the arc cosine of x, that's just going to be x. But that's the only one. The other ones we're going to have to draw triangles. Okay? All right. So let's start with the first triangle. So we need a triangle that has an angle with a tangent of 1. So you draw a triangle where opposite over hypotenuse is 1. Well, that's actually one that we know. That's a 45, 45, 90 triangle. 1, 1, radical 2. Okay? So then you say, well, the cosine then of that angle, so the cosine of this angle adjacent over hypotenuse is 1 over radical 2. Okay? The cosine of the arc cosine, those cancel, leaving you with just x. All right, next. Okay, so we're going back to the same triangle that has a tangent of 1. Now we want the sine of that angle. So opposite over hypotenuse, so 1 over radical 2. Okay, now we need a triangle that has a cosine of x. See, this triangle doesn't have a cosine of x, so we need to draw a second triangle now. So the sine of the arc cosine. So we draw a triangle that has a cosine of x. So that's adjacent over hypotenuse is x. So now we need the sine of that angle. So opposite over hypotenuse. Let's see. Adjacent. Okay, let me make sure. Adjacent over hypotenuse. So opposite. So how did I get that third side? How did I know that radical was the third side?
The Pythagorean.
Pythagorean theorem. Okay? So then that would give us the sine opposite over hypotenuse. And so now to just simplify, we have, so x times 1 over radical 2 minus the radical over radical 2. So you can put those together over 1 radical 2. So just combine the fractions. And you don't have to rationalize the denominator. It's fine just how it is. Okay? All right. So that's a little crazy because you're going to have to combine that. Now, okay, so for your problem, you can use these same triangles here, okay? So for practice 3B, you can actually use these same triangles. But go ahead and try that. All right, Kibri?
I am very, very lost. Can you please help?
Sure.
Thank
You bet. Okay, so the arctan of u, that's going to be your u. And the
So-
cosine of x, that's going to be your v. Those are angles. Yeah.
So, I just barely got all the notes that I missed. So the U is the X and the V is the Y, kind of?
Yeah, well, whatever variable. It's just they're going to be the two angles that you plug in. So
Okay.
some books use X and Y, some books use V and U. It really doesn't matter.
Okay.
Okay. So then you look for the formula of sine U plus V. Okay. So this is the formula that you're going to use. So you want to write that down.
Okay.
Okay, so the sine of u plus v is the sine of u cosine v plus cosine u sine v. All right, so you're with me so far?
Yes.
Okay, so now in place of u, you're going to write arctan 1, and in
Right.
place of v, you're going to write arc cosine x.
Okay. So that's going to be a very long.
Yes, it is.
Okay.
Mr. Strong,
Yes.
with these equations, how do you know when to use a 45, 45, 90 triangle or a 30, 60, 90 triangle?
Well, you really don't know. You don't know until okay. So how, like this, we don't really know we're not drawing these to be 30, 60, 90 or 45, 45, 90 triangle. What you're doing is like on this one, you're drawing a triangle that has a tangent of 1. So if this is the angle, the tangent opposite over adjacent. Okay, so then when you draw that, then you say, oh, that's a 45, 45, 90 triangle because I know the pattern is 1, 1, radical 2. But see, this one is not necessarily, we don't know anything about this one except that we know that it has a cosine of x, so x over 1. So it's not necessarily a special triangle, but it is a right triangle, so we can use the Pythagorean theorem to find the third side, which would be radical 1 minus x squared. Now, is there a question on how I get that?
Yes.
Okay, so with the Pythagorean theorem, you say the sum of the legs of the right triangle is equal to the sum of the squares of the legs is equal to the square of the hypotenuse.
Oh.
So you say 1 square, so x squared plus, okay, I'm going to just call this b. X squared plus b squared equals 1 squared, and then you solve it for b. So subtract 1 squared, or x squared, take the square root, so it's radical 1 minus x squared.
All right.
Okay, so then you have your two triangles. So then you say, okay, so this is the angle that has a tangent of 1. So the sine of that angle is opposite over hypotenuse, so that's 1 over radical 2. Okay, the next one, cosine and arc cosine cancel. So that's just going to give you x. Okay, the third one, the cosine of the arctangent of 1. So back to this triangle, because it has a tangent of 1. So then the cosine of this angle is adjacent over hypotenuse, so 1 over radical 2. And then finally, we need the sine of the arc cosine of x. So this one. So the sine of this is opposite over hypotenuse, so it's just radical 1 minus x squared over 1. So then we simplify that, and so we get radical 2x plus radical 2 times x minus x, 1 minus x squared all over 2.
Is that X under the radical? Or is it outside?
No, it is not.
Okay.
Because it's not up here. All right.
So I have a question. So
Okay.
if instead of it saying arctangent 1, and it was just like tangent 1, would that change it in any way?
Yeah, because see, then you couldn't really draw a triangle. See, then the tangent of 1, that would be like the tangent of 1 radian, and so you could put that in your calculator or whatever.
Jason,
See, the arctangent of 1 is actually an angle. When you say the tangent of 1, the 1 is the angle. Yes, Joe?
triangle, right?
Do you always want us to rationalize the denominator, or
No. Wait. Did I not rationalize the denominator? Oh no.
You did.
No, there was nothing to rationalize there.
You
You mean from
rationalized
here
1
to
over
here.
radical 2. Yeah.
Oh no, yeah, no, I don't think we needed that. Let's see. Okay, so I guess I have it like that.
yeah, that's what I got.
Yeah, that's fine. That's fine. Now, for me to require that, I think would be irrational. Thank you. So let's keep it real. Sorry, okay. I just don't want these problems to be more complex than they have to be. But, all right, just stop. Okay, all right, we'll just stop that. Okay. All right, well, whoops. Okay, let's go on here.
So Mr. Strong,
Yes.
what is the purpose of that? Like, what does that answer mean?
Well, what we're doing is putting the sum of these two angles, the sine of a sum, in an algebraic expression. So not all the time when you apply these formulas are you going to have numbers for angles. So like we've had them where, okay, you found the sine of 45 plus the sine of 30 and whatever. These examples are more like what we deal in calculus. So like even today we were using some of these trig formulas so that we could simplify a problem so that we could do calculus on it. Okay? That's the best explanation that I have for it. Okay. All right. So now this last application is the way to write a sum of sines and cosines as just a sine. Okay. So a sine x plus b cosine x is the square root of a squared plus b squared times the sine of x plus phi. So it's got a new variable there where the cosine of phi is a over the radical and sine of phi is b over the radical. Okay.
Is that still the theta sign?
No, this is a phi. Where the theta kind of swirls up like an O, whereas this phi kind of goes down. So they're different Greek letters. But that's what they use for this formula all the time is this phi. I don't know why they don't put a theta or a y or something like that, but since that's kind of how it's always written. Now, here's the thing. While you're writing this down, let me kind of tell you a little bit of so one day I'm like watching, I don't know, flipping through the channels on TV, and I run across this music program, and this guy's talking about how he can take any any musical sound, any musical wave, and write it in terms of sines and cosines. Like give Mozart an equation. And so it was just really fascinating to me that they would take all these really complicated compositions and they could write it in terms of sines and cosines. Well, so this is actually one step further, is taking everything that's in terms of sines and cosines and just writing it in terms of sines. And so what that means is that every equation, in fact, can always be written in terms of just sine, the trig function. So that's pretty powerful. So let me kind of explain how we use this. Okay. Well, okay. All right. So this is express the function f of x equals sine x minus radical 3 cosine of x in terms of just the sign. Okay, so the first thing to do is actually figure out the radical in those equations. Okay, so the square root of a squared plus b squared. So what would a be in this example? 1. Okay, so the coefficient of the sine. And what would b be?
Radical 3.
Yeah, except it has a
Negative
negative
radical.
with it. And so in the formula, since it's a sine theta plus b sine, you actually put the negative with it. Okay? All right, so a is 1 and b is negative radical 3. All right, so now you figure out the square root of a squared plus b squared. So that would be the square root of 1 squared plus negative radical 3 squared. So that's going to be 1 plus 3 is 4. Square root of 4 is 2. Okay? So the radical is going to be 2. Now, the next thing you do is you figure out what the phi is, the angle. Now, what that is, it's the angle that you're adding to your x. Okay? So you use those two conditions. So the cosine of phi was a over the radical. The sine of phi was b over the radical. Okay? So then you say, all right, so a was 1, b was negative radical 3. And the radical was 2. All right, so what angle has a cosine of 1/2 and a sine of negative radical 3 over 2? So you might look at your unit circle or see if you can figure it out. Well, what quadrant would phi be in?
4.
4.
Because that's where the sine is positive, and the cosine is positive, the sine is negative. So we know we're in quadrant 4. So then what angle would it be?
300.
300. Okay. You could also say negative 60. Either way is fine. Okay, so now you're ready to write down the answer. So then the final answer is 2, the radical, times the sine of, and then either x minus 60, or you could say x plus 300. So 2 sine x plus 300. And that's the final answer. All right? So see if you can do that last practice problem, practice 3C.
I'm confused. Can you help me, please?
Sure. Okay, so what is A?
I believe it's 1, correct?
Correct. And what is B?
1.
So
Negative 1.
what is the square root of A squared plus B squared?
It would just be 1, right? No. 2.
2. So be the square root of 2. Because it's the, so A squared would be 1 plus B squared would be 1. So it's the square root of 1 plus 1. So the square root of 2.
Okay. So it'd be
Oh,
1.
A is actually negative 1. Sorry. Negative 1. I forgot there. So, but we're still going to have the square root of 2 is our radical. Square root of A squared plus B squared. Okay, any questions on that? Okay, so next we got to find the phi. So you say the cosine of phi is 1 over radical 2. And which is radical 2 over 2. The sine of phi is negative 1 over radical 2, or negative radical 2 over 2.
Did you get the radical 2 over 2 by rationalizing?
Yeah.
So you have to rationalize
No.
this?
You could, I just wrote it either way, however you have it on your unit circle. Some people have it as 1 over radical 2. Some people have it as radical 2 over 2. So no, it's just whatever helps you find the angle. So then you say, well, what angle has a cosine of radical 2 over 2 and has a sine of negative radical 2 over 2?
Negative 45?
So that would be negative 45 or 315, however you want to write it.
Is it 2 sine again, though?
No. In front, the coefficient is the radical. So what was the square root of A squared plus B squared?
Radical 2.
So radical 2 goes in front. So it's radical 2 sine, 2x minus 45. Why is it 2x? Because both of these were 2x. So that doesn't change. So it's 2x, and then either minus 45 or plus 315. Okay? All right. Well, that's it for 7.2. We'll start on 7.3. Remember, if you haven't written down the formulas for 7.3, you might want to do that before class tomorrow. Okay? Just so you have those on your sheet already. Okay? All right. Any questions before we drop? All right. Well, you guys have a great day, and we'll see you then.